Okay, here's a small data set with 3 points for X and 3 points for Y. I've already typed those into my calculator, and I'm going to do 2var stats on this. And I see that X bar is 3 and Y bar is 4. And I can find correlation the long way, or as we've done before, I could press stat calc number 8, do linear regression here where L1 and L2 are my X and Y. I'm going to store the regression equation into Y1 by pressing vars, yvars function Y1. And when I calculate this, it'll show me my R and R squared, show me A and B. And if I make a scatter plot of it, L1 and L2, since I've got this equation already in Y1 by virtue of saving it, a zoom 9 will look something like this. Okay, so looking at this line, how good of a job does the line do at predicting? What do you think? It's pretty crummy. It's pretty crummy because I can look at the graph and see that it's pretty crummy. It's also pretty crummy because when I look over here at my R, I see that R is 0.18898. That's terrible. The line does a pretty bad job in this case. Okay. In fact, I'm not even sure that the points are linear because I only have 3 of them. But ever what, I got a small data set. That's okay. So I want to show you some things here, and you probably won't follow why I'm doing this. As long as you can follow what I'm doing, you'll be okay. So let's say that I want to use this equation, and I could write it down here. The equation is y hat, don't forget the hat, 3 plus 1/3 x, and that's just using these things that I got from doing linreg on my calculator. So now I want to ignore these values here in y for just a second, and I want to come up with y hat. In other words, if I take 0 and I stick it in that equation, what does the equation predict for y? 1/3 of 0 plus 3, it predicts 3. If I stick a 3 into the equation, what does the equation predict? 1/3 of 3 is 1 plus 3, that's 4. And if I stick a 6 in there, it's going to give me a 5. Now what's the mean of that? What's the mean of that list? 4? 3, 4, 5, the mean's going to be 4. Okay, so this is what my guess was. This is what my actual point was. So the next thing I want to do, again, the reasons why I'm doing it are less important, but the next thing I'm going to do is find how wrong I was. So I'm going to go y minus y hat. So this is 0 minus 3, 10 minus 4, 2 minus 5, or negative 3, 6, negative 3. What does that add up to? Adds up to 0, right? So it adds up to 0, and that's not a surprise. That's what the line's all about. It's all about balancing that stuff out. So these things here are my residuals. These are called the residuals. That's telling me how wrong I was each time. And it's always going to add up to 0. So previously, how did we handle things when they all added up to 0 all the time? Remember in chapter 1, we ended up squaring them. So let's look at that. Y minus y hat squared. So this is 9 and 36 and 9. And those things add up to, 54? This is a measure of how wrong I was. I don't have to worry right now about 54 watts, but it's just a measure of how wrong I was. If this number was smaller, what would that tell me about my line? That means it's better. If this number was smaller, that would mean these numbers are smaller, which would mean I was less wrong, which would mean my line was better. If this 54 was really big, it would mean my line was really crummy. So we already know the line's crummy, so 54 must be kind of big, at least in context of this problem, but this is a measure of how bad my line was. It's summing up the square of my errors. For the sake of this discussion, I'm going to call this value the sum of the squares of the errors. That's not necessarily a standard term, but that's what I'm going to call it, the sum of the squares of the errors. Okay, now, what if instead of saying use y hat, what if I just said, you know, the mean is 4, so let's just guess 4 all the time. So if I say to you, hey, you x is 0, you say 4, and I say, yeah, but what if x was 4? And every time you just guess 4. So if I give you some information like x, and you use that information to predict y, that's because you're using your y hat line. On the other hand, if you're not going to use the x information, you might as well guess 4 every time. In other words, if x is 0, you're going to guess 4. If x is 3, you're guessing 4. If x is 6, it's 4. You're just always going to guess 4. So let's see how bad of an idea this is. So I'm going to see how wrong I was each time I did that. So this is going to be 0 minus 4, 10 minus 4, and 2 minus 4. So that's negative 4, that's 6, that's negative 2. What does that add up to? 0. Again, not a surprise. That's the way the mean works. That's what's going to go on. So just like before, let's go ahead and square that. So I'm going to go y minus y bar squared. So this is 16, this is 36, this is 4, this adds up to 56. Again, this is a measure of how bad of an idea it was just to guess the mean every time. And we see it's a little bit worse than using the equation, because that number, that 56, is a little bit bigger than 54. I'm going to call this the sum of the squares of the differences from the mean, SSM. So what I'm going to do next is say, what if I took SSM minus SSE divided by SSM? What does this look like to you from maybe another class? Yeah, it's kind of like percent error, right? So this is telling me, this is measuring how much better this method was than this method relative to the magnitude of my numbers. So I can't do this in my head. This is going to be, obviously I could do the top of that in my head. That's 2. 2 divided by 56. This is 0.0357. You notice anything about that? That's r squared. That's what r squared is. Now, I don't necessarily advocate calculating it with the method I just used, but my rationale for showing you this is to teach you that r squared is a percent. It's like percent error. This is telling me how much better off I am using y hat than just using y bar. So you tell me, am I a lot better off? No, this is only 3.57. And the sentence that I'd like you to learn is this: blank percent of the change in y can be explained by or predicted by the LSRL of y on x. So in this case, 3.57% of the changes that occur in y could have been anticipated by using that regression line. Which regression line? The one that takes the y's and maps them onto the x-axis, the y on x. Now, how would I actually recommend you calculate r squared? I'd either recommend you do linear regression, just like we did on the calculator here, or remember that r squared is simply r squared. So if you figured out r, you could just square it and get r squared. The nice thing is r squared is a percentage. R is not a percentage. So how do you get from r to r squared? You square it. How do you get from r squared to r? Now see, it's a little more complicated than just square rooting it. Because when you square root something, what do you have to do? Worry about if it's positive or negative, right? Because r's can be negative. So how do you know? How do I know if this is if I gave you this r squared, I square root it, how do I know if r is positive or negative? I could look at the graph. Yeah, if the points are going uphill, there's a positive association, my r is positive. If it was a negative association, I would put the negative in front of it. What about looking at the equation here? Yeah, look at the slope of the equation. If the slope of the equation is positive, r has to be positive. So going from r to r squared is super easy, just square it. Going from r squared to r is not hard, but not only do you have to square root it, you have to worry about is it positive or negative. And don't put plus or minus in the front of it. Make a decision. Is it plus or is it minus? Look at the graph or look at the equation to figure that out. So this is a little bit of an explanation on what in the world r squared is, how you might go about calculating it if you were so inclined, which I don't suspect you are, and a good sentence that's probably worth memorizing to explain it.